A very good morning, students. Now today the topic of the class is photoelectric effect in terms of chemistry. अब इस photoelectric effect में दो important words हैं. The first word is photo and the second word is electric. Photo का मतलब है light और light से we would be basically talking about the visible light और electric का मतलब है electrons. And we talk about the electrons is the information that we already know about electrons. Electrons के बारे में जो दो information है वो क्या है? The charge is 1.6 10 to the power minus 19 coulombs, negative है of course, and the mass is 9.1 10 to the power minus 31 kgs. ये दो values बेटा class 11th and 12th में आपको याद होनी चाहिए. So when we talk about an electron, it has a negative charge, we represent it as small e. The charge is itna coulombs and the mass is 9.1 10 to the power minus 31 kg, which is negligible for your information in comparison to protons and neutrons. Now coming to the light part. The electromagnetic spectrum consists of all possible radiations: gamma rays, X-rays, ultraviolet rays, infrared rays, micro rays and radio rays. Out of all these microwaves and radio waves, out of all this, our interest is in this small part which comes between ultraviolet and infrared. This small part is your VIBGYOR, that is the visible light. So when we talk about the visible light falls between ultraviolet and infrared. You very well know we are talking about VIBGYOR. Violet, indigo, blue, green, yellow, orange and red. Fine. This is your VIBGYOR, the components of light visible to us. Now when we represent this, you should always represent it like this. Pay attention. What have I done? Pay attention. What have I done? I am increasing the wavelength, which means when I'm talking about it, the wavelength of these lights is smaller while the wavelength here is larger. If we talk about the wavelength of the red light is around 700 nanometers while the wavelength of the violet light is around 400 nanometer. So, जो light आपको visible है is in between the range of 400 nanometer to 700 nanometer. Now, what else do we know about light? What we know about light is that you have the wavelength is this, which is the information given to you, and we find that wavelength increases as you move from this side. You very well know energy of a photon is equal to h mu, where h is the Planck's constant and mu is the frequency. E is given by hc by lambda, which means energy of a photon, which is a particle of light, is inversely proportional to lambda. तो अगर हम इनका compare करें, we talk about the energy component of the photons. अगर हम energy of photon की बात करें, तो out of your VIBGYOR, which has the highest energy, lambda कम होगा तो energy ज़्यादा, यानी इसकी energy will be maximum violet, and here you would have it to be minimum. Is that clear? So when we talk about the light, radiations of the visible light, we say when we talk about energy, you have energy component, maximum is for violet and minimum is for red. Fine. Similarly, energy, as you can see here, is directly proportional to the frequency of light. So in this case, if the energy here is maximum, so what we can say is frequency here is maximum and frequency here is minimum, which means red की frequency सबसे कम होगी, red का wavelength सबसे ज़्यादा होगा, red component would have the minimum energy. Coming to the wave number. Now what is wave number? Wave number is represented like this, which is nothing but inverse of wavelength. So wave number is equal to inverse of wavelength. तो जहाँ wavelength ज़्यादा होगी वहाँ पर wave number minimum होगा. Wavelength कहाँ ज़्यादा है? यहाँ पर अगर wavelength ज़्यादा है तो wave number is minimum for this end of the visible light, while wave number is maximum for the violet section of the visible light. Is that okay? Now, let's talk about energy of the photon. When we talk about energy of the photon, we represent this energy of a photon in terms of units called as EV, which is electron volt. So, when I am going to talk about the energy of each photon, I can calculate. कैसे? E is equal to h into mu. E is equal to hc by lambda. Lambda के values I have. For the green component also, I have the value of roughly 550 nanometer. Since I have the wavelength for all these components, I would also know the energy of these components. Is that fine? तो हर एक लाइट के फोटोन की एनर्जी हमारे पास है, which means when I talk about the violet light, I have the value of its photons energy. The violet light का nanometer wavelength इतना है, तो energy can be calculated by hc by lambda. If you calculate the energy of the photon, we find that for the violet light, it roughly comes out to be 3.1 electron volts is for the violet component and 1.7 electron volt is for the red. Fixed नहीं होगा बेटा, it is a range. Red component is around 700. It could be 690, it could be 680, somewhere around that range. So for roughly, if we talk about the electron volt, if you substitute these nanometer values here, you can get the energy of the photon, which comes in the range of 1.7 eV, while for the violet component, it is around 3.1 eV. Similarly, for the blue component or the indigo component, if we see, the energy is 2.8 eV. If I talk about the orange component has 2 eV. Is that clear? So when we talk about energies, you can calculate the energy for each and every light. The yellow component has around 2.1 eV. So when we increase the wavelength, as the wavelength increases, energy should decrease, and it is decreasing. The energy is maximum here 3.1 eV and the energy for each photon is minimum here 1.7 eV, which means agar violet color ki light hits, its energy is this much. Red colored light if hits, the energy is this much. Energy of a red radiation is lower while the energy of a violet radiation is higher. I repeat, how do you get these values? These values are got when you get the value of energy by multiplying the Planck's constant. The c is the frequency of the velocity of light, 3 into 10 to the power 8, और lambda in nanometers डाल के उसको meters में convert करना पड़ेगा, and then you can get it into electron volts also. Also, if you want to transform the electron volt into joules, then what do? You should know that you can transform electron volt into joules by the formula 1 eV is equal to 1.6 10 to the power minus 19, and you get it in joules. What have I done? I have multiplied it by the charge of the electron. So if you want to transform an electron volt into joules, just multiply it by the charge of the electron. So this is the information about light that we have, and now we move on to the topic of the day, photoelectric effect. For the photoelectric effect, this information was required, that for the violet component, energy is maximum, wavelength is minimum, energy of the photon is of this order, while when we talk about frequency would also be maximum, wave number would also be maximum because the wavelength is minimum. Fine. Moving ahead to the next actual topic of the day, which is photoelectric effect. Now, this is the experiment which was performed for identifying the concept of photoelectric effect. Now, this photoelectric effect, as the word says, light say electricity, which means light say flow of electrons. So whenever we want to talk about the photoelectric effect, our interest is that how can we get the electricity from the light. And this experiment was performed by Hertz, and he had taken a vacuum tube. In this vacuum tube, he had placed a metal. surface, and this is called as the detector. Pay attention to the connections. You have a positive terminal here, यानी ये positive है. You have a negative terminal here, so your metal has a negative charge. Fine. Now, after this, what was done? There were radiations, light waves hit on this surface. Blue light डाला, red light डाला. Blue light डालने से it was found the electrons were found to move. Electrons were ejected out, and the electrons are what charged? Negative. So electrons will move towards the detector, the positive terminal. Blue light के डालने से the electrons were started to move, and we found a reading in the emitter. Hence, it was concluded that some lights do cause electron ejection from a metal surface. Now, when it was the red light, no electron was visible. No passage of electron happened, or there was no emitter reading detected. Since there was no emitter reading detected, we come back to the conclusion that we had done, that red light ka energy is minimum 1.7 electron volts, while violet light ka energy is maximum 3.1 electron volts, which means if you hit the metal surface with 1.7 electron volt, electron was not ejected out, while if you hit it with 3.1, this is around 3.1 electron volt, the electron was found to be ejected out, which means electrons ejection depends on the energy of the light, which means the energy required given by the light photon is the key to the ejection of electrons, is the concept of photoelectric effect. Now, when we talk about metals, now which metals? How do you define metals? Metals have to lose electron. Can I say they have electrons are loosely held? That means they can be easily removed. Now, in your periodic table, where do you get the metals? Metals in the periodic table are towards the left and bottom, which means periodic table पे left में जाओ, फिर bottom में जाओ. I am talking about group 1. So when we talk about group 1 members, which are the group 1 members? You have lithium, sodium, potassium, rubidium and cesium. We will not be talking about francium because francium is radioactive, which is unstable, so we will not talk about it. Talking about lithium, sodium, potassium, rubidium, cesium, these are metals which are reactive metals. They have got electrons loosely held. Now, out of these, which out of them is most metallic? Cesium. Now, why is this most metallic? Because this is largest in size. Size बड़ा होगा तो electrons are not held tightly. Nucleus से electrons are far away, they can be easily lost. This term we also use as least ionization energy. So, when we talk about which metal, the ideal metal would be cesium is the best. After that, you would have rubidium. After that, you would have potassium. After that, you would have sodium. Lithium is too small. So, the metals which will show photoelectric effect, best metal would be cesium. After that, these metals. Now, the reason why they are good metals, because these metals should have electron lost. It should be easy, which means they have a low ionization energy. Now, this term you would do in periodic classification. Low ionization energy means energy required to pull out electron is least. You can refer to the channel for the periodic classification where you would get the concept of ionization energy in detail, and you can go through that in case you want to read further. So, the best metal is cesium. Now, moving ahead, let us talk about photoelectric effect further in detail. Now, I have taken metals. Now, let this particular metal be sodium. Okay? And when I talk about sodium, it was found that if I use the red colored light, here are red light, bada wavelength. If I use red light and hit the sodium metal surface, there is no electron released. When I know the energy of the photon of the red light is 1.7 eV and I find there is no electron released, which means no photoelectric effect. All sodium metals do have loosely held electrons. Metals do have loosely held electrons in them, which can be lost. Now, coming to the next concept, if I use a green light, when I use a green colored light, comparatively the wavelength will be less and it hits here. This green colored light, as soon as it hits, I find that the electron is ejected out, which means photoelectric effect is observed. Now the question is why? Green light photon will have energy of the order 2.2 electron volts, which means 1.7 say electron did not eject, but 2.2 say electron ejected, which means electron removal requires energy. Now why does electron removal require energy? Because electron is held on to the nucleus. Nucleus ne pakad to rakha hi hai. It is loosely held, but still there is energy required to remove it. Fine. Now coming to cesium. If I have the cesium as the metal. Now this cesium metal is again an alkali metal. This is the best metal for photoelectric effect, but still, isme bhi, if I use the red light, there is no photoelectric effect, which means again the energy requirement is more than 1.7 electron volts. Fine. So now I use the yellow light. When I use the yellow light, I find with the yellow light, the electron is ejected out. This was my electron and it is ejected out, which means yellow light could be having a higher energy, which is enough to excite the electron from the cesium element. So when we talk about cesium, we find with the yellow light has 2.15 electron volt, and for cesium it was okay. So when would photoelectric effect happen? If the energy of the photon is enough to break the electron away from the nucleus and cause it to move. Fine. So you can have understood that the alkali metals easily show photoelectric effect. Similarly, if I take potassium. Now when I talk about potassium as a metal, it is found that in case of potassium, we find with the orange light, the photoelectric effect does not happen. Orange light has 2 electron volts ka energy. Photon energy is 2 electron volts. No photoelectric effect was observed. But with the yellow light, when we talked about the yellow light, it was found that the yellow light has what energy? Yellow light's energy is 2.1 electron volts, and it was found that with 2.1 there is a electron ejection, which means potassium में से electron निकालना is easier than that of sodium, which is true क्योंकि potassium का size बड़ा size है तो electron can easily be lost. So alkali metals में cesium is the best for photoelectric effect, then rubidium, then potassium, then sodium, and lithium does not show photoelectric effect. Fine. Now moving to the details of photoelectric effect, let's come to the details using a potassium metal. Now, before I actually go to this part of it, I need to do one more concept, which is supposing you have this as the metal and it has got some free electrons in it. Fine. This is your metal which has a low ionization energy, or it can easily lose electrons. Fine. When we talk about such a metal that it has a low ionization energy, means it can easily lose electrons. So when we drop light onto it, if you have any light, I'm generally talking about light, when I have some light put on it, these are the light waves which hit on the surface of the metal. When these light hit on the surface of the metal, it is found that sometimes the light, when hits the electron, then it pushes the electron first to the surface. पहले electron just बाहर आएगा. This is one energy. This energy which is required to just move the electron outside, is called as the work function. Now after this, now the electron will move away and you would have the electron moving away with some kinetic energy. Which means your light had, this was the energy of the photon. And the energy of the photon hits onto the electron and we find the energy is used in two things. पहला function, electron को यहाँ से बाहर लेके आओ, just to remove it from the surface, which is called as the work function, and after that you require the kinetic energy. So your energy of the photon is used for two things. One is the work function, just to remove the electron from the metal, bring it onto the surface, and second is for the mobility of the electron, that is the kinetic energy of photoelectron. These are the two main functions of the energy given by the photon. Now, energy of the photon हम कैसे निकालते थे? E energy कैसे निकालते थे? H mu. Now, work function is also energy. This also can be calculated by H mu naught. Mu naught refers to the threshold frequency, the minimum frequency that is required just to remove the electron from the metal surface onto the inside the metal to the metal surface. Kinetic energy कैसे निकालते थे? Half mass of electron, velocity of electron square. Fine. इसमें से mass of electron you already know, 9.1 10 to the power minus 31 kg. H की value 6.63 10 to the power minus 34 kg meter square second inverse. Photon की energy would be provided maybe. V stands for velocity of photoelectron. Fine. Now readjusting this expression, can I say H mu minus H mu naught is equal to the kinetic energy of photoelectron? From here, H mu minus H mu naught gives me the kinetic energy of the photoelectron. Can I further writing H common? Mu minus mu naught, the threshold frequency, is equal to the kinetic energy of photoelectron. So, if you want to find out the kinetic energy of the photoelectron, you can substitute these values. H is the Planck's constant, mu is the frequency of the photon of light hitting the surface, and mu naught is the threshold frequency, the minimum frequency required. This is the minimum frequency needed for photoelectric effect to happen, that is to make the electron move from the inside of the metal to the surface. Surface says to jayega. Fine. So this is the formula that we use for numericals. H is the Planck's constant, mu is the frequency of the light, H is again the Planck's constant, this is the minimum frequency required, and this is the kinetic energy. Now, supposing there is a question where it says that the kinetic energy is 0. Suppose karo, there is a question, we know H mu is equal to H mu naught plus kinetic energy. Suppose karo it is given that the kinetic energy of the photoelectron is 0. इसका क्या मतलब? इसका मतलब the electron is just here, बस उसके आगे energy ही नहीं है. The total energy of the photon is used just for this, which means here this is 0, which means energy of the photon was used, we know it, for work function, that is just to remove the electron and make it come to the surface, plus the kinetic energy of the electron. Now, if this kinetic energy becomes 0, so we know that energy of the photon in that case would be equal to work function, which means H mu would be equal to H mu naught, which means frequency of the photon is equal to the threshold frequency. Fine. So, all the energy that was given by the photon is just used for work function. And what is work function? The energy required to make the electron move from the bulk of the metal, bring it onto the surface. This work function is fixed for the metals. This work function is a fixed value for metals. Now, we very well know work function is the energy required to pull out the electron. So, we know cesium will have a minimum value because this is largest in size and the electron removal is the easiest. And in group 1, if we talk about, you have cesium का energy would be, work function would be minimum, rubidium का ज़्यादा, potassium का और भी ज़्यादा, and sodium would be maximum when we talk about the work function values. Work function in books is, NCERT gives it at W0, and the other books you would find it is given as 5. So don't get worried. You would find the formulas could be like this: H mu is equal to H mu naught plus half mv square, where mass is of the electron, or it is at times written as E, the energy of the photon, is equal to the work function plus kinetic energy of photoelectron. Fine. So moving ahead with the concept ahead, we come to the second part of it. Now this is what I was trying to help you out with. Now let us take a metal which is potassium, and it has a work function of 2 eV. 2 eV ka matlab the energy required just to bring the electron to the surface is 2 eV. Fine. Let us take, these are the electrons which are hit by the visible lights. There are loosely held electrons onto the potassium surface, and they have to be hit by the light. Now we very well begin with the first light given, red. ध्यान से देखो बेटा, red को ऐसे बड़ा बनाया because the wavelength is longer, because energy is less. इसका wavelength maximum, energy minimum. जबकि इसमें देखो wavelength is minimum, low, so the energy would be high. Fine. Now let us talk about red. Red light ka, the energy is of the photon is equal to 1.77 eV. When this light hits the metal here, then it is found there is no photoelectric effect, which means this light is unable to do any photoelectric effect. No electrons are emitted. अब light की energy बढ़ाते, we move to orange. Orange light has energy equal to 2 eV, and the work function of potassium, I have taken it to be 2 eV only. So if the work function of the metal is 2 eV, ka matlab this energy would be used up to do what? Just to cause this would go here. Bas. But kinetic energy would be 0. In this case, kinetic energy of the electron is 0, because all the energy has been used only for the work function, and the electron moves here. Coming to the yellow component. Yellow component ka energy, I hope it's visible. The energy is, for the yellow component, is 2.25 eV. If it is 2.25 eV, तो इसका मतलब पहला electron will first move on to the surface. This will require how much energy? 2 eV. Now you're still left with 0.25 eV. So this electron will definitely move out, and you would have it with 0.25 eV is the energy which is used for the kinetic energy. Fine. Coming to the green component. The green component of the light has the energy of around 2.3 eV. If it has around 2.3 eV, then the first step would be to make the electron move up. This will require only 2 eV. You are left with 0.3 eV. So again you would find photoelectric effect. You are using 0.3 eV for kinetic energy. Coming to the blue component. The blue component ka energy is of the order 2.8 eV. So again this would cause the electron to move upper. This energy required is only 2 eV. बाकी कितना बचा? 0.8 eV. This 0.8 eV is what will be used for kinetic energy. Coming to the last part of the light. When I talk about the last part of the light, so referring to the last component of light, which is the violet component, the violet component has least wavelength, hence maximum energy, which is 3.1 eV. Now utilizing this light. Now if I use this light, as you can see, I would be using a very low wavelength. And it hits here. When this hits here, the first step is the required energy to move it to the surface, which is only 2 eV. I'm still left with, this was 3.1 eV ka photon. I'm still left with 1.1 eV. And so you have 1.1 eV is used for the kinetic energy of the photon.